Alright, so let's work on some problems for redox reactions. This first one deals with potassium dichromate reacting with water and sulfur. So when looking at redox reactions, one of the ways that you can initially recognize if you have a redox reaction is to look for compounds that are occurring as their elemental forms. So if we look on the equation, we can see that sulfur is present just in its elemental form. It's not bound with any other molecule. And so we know that elements in their elemental form do not have any charge that are associated with them. Alright, so we see our sulfur here, and sorry I don't have my tripod with me, so I have to be careful when I'm doing the filming today. But when sulfur is in its elemental form, the charge state is going to be 0 on that. So this is true for any of the elemental forms. So you have to remember that some elemental forms take place as diatomic molecules, especially those gases. So when we have oxygen gas or nitrogen gas or chlorine gas, these are all elemental forms of those compounds, and the charge state on those atoms is going to be 0. So remember, when you're looking at your equations, if you've got any diatomic molecules that exist, like O2 or H2, their assigned oxidation number is also going to be 0. So that's one way that you can recognize when you have redox reactions. Typically on one side of the equation you're going to have an element in its elemental form, and then on the other side of the equation you'll have the element in combination with another molecule. In this case, sulfur is recombining on the left side, from the left side of the equation as elemental sulfur to the right side of the equation as sulfur dioxide. So this is a good indication that the charge on the sulfur is probably changing. So we can walk through the oxidation numbers and now see for sure which one is being reduced and which one is being oxidized, and assign our reducing agents and our oxidizing agents. So for each of the compounds, we're going to draw charge boxes on top, and we're going to find the oxidation numbers for those compounds. Let's start with our potassium dichromate. So for our potassium dichromate, we can assign what we know about the formula. So we know that oxygen is always going to take on that -2 charge, and so we've got -2 right here. We know that there's 7 of those oxygen molecules in there, and so we've got a total negative charge on our molecule of -14. We can also accurately assign the charge state of our potassium. So we know potassium, being in group 1, can only take on the oxidation state of +1. So we know we've got 2 of those, and so we've got a positive charge on our molecule so far of +2. So we know the overall charge on our molecule as well is going to be 0. So we can set our entire equation to 0. We've got 2 chromium ions, and we don't know their charge state. So our overall equation is +2 plus 2x minus 14 has to equal 0. So if we solve for this, what we'll find is, so when we solve for this, we can see if we assign +2 plus 2x minus 14 equals 0, and we go ahead and we solve for this equation, we'll get this down to x equals +6. So on our chromium ion then, we can assign all of these oxidation states to the chromium, the potassium, and the oxygen. So we know the oxidation state on potassium is +1. We know the oxidation state on each chromium is +6, and we know the oxidation state of oxygen is -2. So now we're going to do this for the other compounds in here. We already know that sulfur is in its elemental form. It's going to be 0 charge. The oxygen in our water molecule is -2. The hydrogens are each +1, and there's 2 of those. So the oxidation state on our hydrogen is always +1. That's one of our rules. And now we can go to the other side of the equation and we can assign oxidation states over there as well. So let's move over there. Okay, so now we've got SO2. So let's look at our sulfur dioxide. So in this case, we can draw our charge states above here. So when we do that, we can assign oxygen as the more electronegative element is going to get its preferred charge state. So that's going to be -2. There's 2 of those atoms. So you get a total charge on this molecule of -4. This is going to have a total charge on the molecule of 0 because there's no charge indicated here. And then we don't know what the charge is going to be on the sulfur yet, so we put X there. We know that there's 1 atom, and so we can say 1x minus 4 equals 0. And solving for X, we see that sulfur has to take on the +4 charge. So remember, oxidation numbers are just assigned charges. They're kind of these pseudo charges just to keep track of where the electrons are shifting in the molecule. So sulfur doesn't really take on a positive charge. It's just a number that we can assign to it. But it's the state of the atom. So if we look at how it's changing across the equation, we can see that sulfur is going from a 0 charge to a +4 state. So we know from the left to the right, so we can see our sulfur is getting more positive. So what does that mean about the electrons around that sulfur? Is it losing electrons or is it gaining electrons? Hopefully you said it's losing electrons, because if it loses electrons, it's going to become more positive. And so we know when you lose electrons, you have to be Leo, right? That's the Leo part of the equation. So our sulfur going to sulfur dioxide is the oxidized component, right? It's losing electrons, becoming more positive. So this is our Leo part. So what does that make it? The oxidizing agent or the reducing agent? If it's going to give those electrons to somebody else, it's also going to be the reducing agent. Okay, so let's take a look at the rest of our equation. Let's see how our chromium is actually going to change on the other side of the equation as well. So let's look at our potassium hydroxide first, since that's the next thing. So we know that oxygen, again, can be assigned a -2. Hydrogen is always going to be a +1. And our potassium is always going to be +1 because it is in the group 1 elements. And we say that that balances out. We can also check out our potassium and hydrogen on the other side of the equation. And we can see that they maintain that same charge. So because they maintain the same charge, there's no oxidation and reduction of those atoms going across our equation. So now we need to evaluate what happened with the chromium. So if we go back over here, our last molecule contains our chromium, and so we can evaluate this molecule as well. So if we draw our charge box on top, so if we're evaluating our chromium, we can assign the -2 oxidation state to oxygen. We know there's 3 atoms of oxygen present, so we've got a total negative charge of -6 on our molecule right now. So if we assign our chromium, we don't know what the charge is going to be yet, but we do know that there's 2 atoms of chromium in our molecule. So we can set up our equation, and it's neutrally charged because there's no charge indicated. So we've got 2x minus 6 is going to equal 0. If we end up solving for x, we can see that x has to be +3. So what has our chromium done from one side to the other side? Over here our chromium is +6. So really in this molecule, as it's gone across the equation from the potassium dichromate to the other side over here, we can see our chromium was a +6 state for each of those chromium ions on the left side. On the right side, it's now +3. So has this gained or lost electrons? So we are getting more negative or less positive. So to do this guy had to actually gain the electrons. So if it gains the electrons, it's the GR part of the equation. So this one has gained electrons, so there's the reduced component. So our potassium dichromate was actually reduced to the chromium molecule on the other side. So this is the reduced component. So when things get reduced, they act as oxidizing agents because they're oxidizing some other molecule, in this case the sulfur. So this guy is going to be the oxidizing agent. So if we look at our entire equation one more time, we could say that this guy is the oxidizing agent. It is also the GR part of the equation, so it is the reduced component, or it's what's going to get reduced. This guy is the reducing agent. It is going to lose electrons, and it's going to give them to the potassium chromate to change the chromium molecule on this side from the +6 state to the +3 state. So this one is the LEO part of the equation. It is the oxidized component. So that is one example of a redox reaction. We'll do another one here as well.